Good day, everyone. So today, our the topic that we are going to tackle is on how to use JAM movie in statistical analysis. So our objectives at the end of this discussion, you're expected to be able to identify the appropriate statistical tools for analyzing quantitative data and use the JAM movie software effectively in processing and analyzing your data. So, what is statistics? First, we have to really know what is really statistics. So, statistics is defined as the science of collecting, organizing, analyzing, and interpreting data in order to make decision. So, there are types of data sets, but we have first need to define what is data. Data consists of information coming from observations, counts, measurements, or responses. And we have the four types of data sets. We have the population, parameter, sample, and statistics. Population is the collection of all outcomes, responses, measurements, or counts that are of interest. Parameter is a numerical description of what is populations or the characteristics of population. And the sample is a subset or part of a population. So, like you're just getting a portion in the population to collect your data. And on the other hand, statistics, just as parameter used to describe population characteristics, statistics also is a numerical descriptions of a sample characteristics. So there are branches of statistics. First, we have the descriptive statistics. It is a branch of statistics that involves the organization, summarization, and display of data. The inferential statistics, on the other hand, is the branch of statistics that involves using a sample to draw conclusions about population. So there are types of data. We have the qualitative data and the quantitative data. Now, what are the differences between these two datas? Um, Qualitative data is consists of attributes, labels, or non-numerical interests. So it is more like identifying key themes and patterns. But on the other hand, quantitative data is consists of numerical measurements or counts. So this where we can also use a lot of statistical tools to arrive in a certain conclusion. We have the levels of measurement. We have the nominal, ordinal, interval, and ratio. And this is very important to know. Nominal is a qualitative data, which are categorized using names, labels, or qualities, and no mathematical computations can be made at this level. Ordinal is a qualitative or quantitative data, both quali and quanti, which can be arranged in order, ranked, but differences between data entries are not meaningful. Interval can be ordered data, and meaningful differences between data entries can be calculated, and where zero entry simply represents a position on a scale. And the entry is not an inherent zero. Zero does not mean none, but just a placeholder, label or value, not a real absence. Now let's go down to the fourth level of measurement, which is the ratio. It is similar to data at the interval level, with the added property that a zero entry is an inherent zero, wherein a ratio of two data values can be formed so that one data value can be meaningful expressed as multiple of another. So these are the example of level of measurements. We have the nominal, ratio, interval, and ordinal. Now let's go down to Cronbach alpha. Cronbach alpha used to measure the internal consistency, reliability of a set of items in a test, questionnaire, or scale, indicating how well the items consistently measure the same underlying construct. But we also need to met assumptions to use this. First is items measure a single underlying construct or unidimensionality. Second is items are positively correlated with each other. Third is data are continuous, strict assumption, or treated as continuous, or common for Likert scales. And the fourth assumption is no major measurement errors or badly worded items that violate item consistency. So this assess or intervals of data interest with account of the number of interests in each class. Frequently count of a class. It is the number of data interest in the class, and the relative frequency of a class is the portion or percentage of the data that falls into that class. So the formula of relative frequency is equal to class frequency divided by sample size, or is equal to F divided by N. Relative frequency of a class. It is the sum of the frequencies of that class and all previous classes. Note that cumulative frequency of the last class is equal to the sample size, or N data. So yeah, the graphs of the let's go down to the graphs of the frequency distribution tables, where we have the histogram bar graph, pie graph, and donut, QQ plot, and more. While in this in frequency distribution tables or graphs, we can use many applications. One of them are Jamovie, Google Sheet, and SPSS. And these are the example of those applications. First, we have this jump movie, which really look like quite simple, and we have the SPSS, which also like a simple one. What I like more is the Google Sheet because it is like it's not two dimensional. It is like more like of a 3D, which is really really good as a visual representation of data. Now let's go down to descriptive measures. Measures of central tendency are numerical descriptions that identify the center, middle, or typical value of a distribution. These are the arithmetic mean, weighted mean, median, and mode. Measures of variation describe the amount of dispersion or spread in a data set, indicating how much the data values differ from the mean or from each other. These are the range, variance, and standard deviation. So in descriptive measures, while measures of center tell you where the data are located, summarizing the data by identifying a single value that represents the middle or most typical point of the distribution. Measures of variation tell you how much the data values differ from one another. And variation describes the degree of dispersion or scatter in a set of data, helping you understand consistency, reliability, and how widely values deviate from the center. Like, for example, it is really skewed to the left or skewed to the right. That depends on the data. Next is we have the measures of position. Measures of position describe the relative standing of a data value by showing its rank, percentage, location, or distance from the mean in standard deviation units. These are the fractiles such as quartiles, deciles, and percentiles. It allows you to interpret individual values by identifying the rank, percentage position, or standard score location. I will also teach you on how to draw a box and whisker plot. First is to find five number summary of the data set. Second is construct a horizontal scale that spans the range of the data. And the third one is plot the five numbers above the horizontal scale. And then draw a box above the horizontal scale from Q1 to Q3 and draw a vertical line in the box at Q2. Then the last one is draw whiskers from the box to the minimum and maximum interest. So here is the example of that illustration on illustrating the box and whisker. Next is we have let's now go to the shapes of distributions. This we have actually four types of distributions. We have the symmetric one. It's like a normal distribution. It's a bell shape. And then we have the uniform or rectangular. We have the skewed to the left, which is negatively skewed, and skewed to the right, which is positively skewed. So um, discrete and continuous probability distributions. In random variable x, it represents a numerical value associated with each outcome of a probability experiment. Discrete has a finite or countable number of possible outcomes that can be listed. And then in discrete probability distributions, it is a listing of all possible values of a discrete random variable along with their corresponding probabilities. Continuous has an countable number of possible outcomes, represented by an interval on the number line. And then continuous probability distributions is listing of all possible values of a continuous random variable. Normal distribution, it is a continuous probability distribution for a random variable x where its graph is called the normal curve. So here we have the empirical rule in normal distribution. Uh, for data with a symmetric bell-shaped distribution, the standard deviation has the following characteristic. First is about 68% of the data lie within one standard deviation of the mean, which you can see it in the left side, these inflection points. And then the second one is about 95% of the data lie within two standard deviations of the mean, which you can see in the second picture. And the third characteristics is about 99.7% of data lie within three standard deviations of the mean, which you can see in the last picture. Now let's go down to the sampling distributions and central limit theorem. So to define sampling distribution is the probability distribution of a sample statistic that is formed when samples of size n are repeatedly taken from a population. So if you are repeatedly taken sample size from that certain population, it would likely be that your distribution would become normal. So next, we have to discuss the central limit theorem. It is to form the foundation for the inferential branch of statistics. So the central limit theorem, it states that for a sufficiently large sample size, the sampling distribution of the sample means will be approximately normal, regardless of the shape of the population. It tells us that when we take repeated random samples, as what I said earlier, the distribution of the means become more normal as sample size increases. And the mean of the sample means equals the population mean. The spread of the sample means becomes smaller as sample size increases. And we can use normal probability methods to make inferences about population means. So we have the normality test. So the function of normality test is like it is used to check whether a set of data comes from a normally distributed population, which is an important assumption for many parametric tests. So here are the common normality test. It includes Shapiro-Wilk test, Kolmogorov-Smirnov test, Anders okay na. I-edit lang ako na. Anderson-Darling test. It gives more Shapiro-Wilk test is a very common and powerful for small to pag-focus nga laan. Ay ako na i-delete. Di rin ako tabang. Stop na. So now let's go down to normality test. Normality tests are statistical tests used to check whether a set of data comes from a normality distributed population, which is an important assumption for many parametric tests. So here are the common normality tests include. We have the Shapiro-Wilk test, we have the Kolmogorov-Smirnov test, and we have the Anderson-Darling test. So Shapiro-Wilk test is a very common and powerful for small to moderate samples. And the Kolmogorov-Smirnov test with Lilly force correction. It compares the sample distribution to a normal distribution. And then last, we have the Anderson-Darling test. It gives more weight to the tails of the distribution. To proceed, we have the confidence intervals. So, point estimate, it is a single value estimate for a population parameter. Note that the most unbiased point estimated of the population mean is the sample mean. So the level of confidence is the probability that the interval estimate contains the population parameter. So, for example, in this illustration, we can see that the horizontal segments represent 90% of confidence intervals. For different samples of the sample size in the long run, 9 of every 10 such intervals will contain the mean because when you do the test, all of them, except one, is not included. So this one is what we call the outliers. So now let's go down to hypothesis testing. Hypothesis test, it is a process that uses sample statistics to test a claim about the value of a population parameter to make informed decision. So statistical hypothesis, it is a claim about a population parameter that can be tested using sample data through the procedures of hypothesis testing. So what is the purpose of hypothesis testing? Why in research we do this hypothesis testing? So because to use sample data because in sample data we need to decide whether there is enough evidence to reject or fail or to reject the claim. So we have the two types of hypothesis. We have the null and alternative. In null hypothesis, a statement of equality involving the population parameter and a hypothesis that is assumed true unless there is sufficient evidence to the contrary. So if there is no sufficient evidence, then the null hypothesis is not proven. Let's dig deeper to the alternative hypothesis. It is a statement that must be true if the null hypothesis is false and reflects the claim that the researcher or study aims to support. So what is the role of a statistical hypothesis and hypothesis testing? So the first point is hypothesis testing uses sample statistics to evaluate the truth of claims about population parameters. Evidence is judged based on the significance level alpha. The conclusion is either to reject the null hypothesis or fail to reject the null hypothesis. We never accept null hypothesis. We only fail to reject it if the evidence is insufficient, like what I've said earlier. There are there are two types of errors. But first, let's just define errors in hypothesis testing, which are mistakes that can be made when using sample data to make decisions about the population. So, first, in type 1 and type 2 error under the null hypothesis, the type 1 errors occurs if the null hypothesis is rejected when it is true, and type 2 error occurs if the null hypothesis is not rejected when it is false. Now we have that also the type 1 and type 2 error in alternative hypothesis. The first point is false positive. It is rejecting a true null hypothesis. Second is false alarms are harmful and led to wrong decisions and unnecessary actions, especially about safety concerns. And the type 2 error is false negative, means failing to reject a false hypothesis or the null hypothesis. And the second point is missing a problem leads to danger or loss of opportunities. So in level of significance, you will reject the null hypothesis when the sample statistic from the sampling distribution is unusual. You have already identified unusual events to be those that occur with a probability of 0.05 or less. When statistical tests are used, an unusual event is sometimes required to have a probability of 0.10 or less, or 0.5 or less, or 0.01 or less because there is variation from sample to sample. There is always a possibility that you will reject a null hypothesis when it is actually true. In other words, although the null hypothesis is true, your sample statistic is determined to be an unusual event in the sampling distribution. You can decrease the probability of this happening by lowering the level of significance. So, this is now the importance of level of significance to really test our hypothesis to avoid in making wrong decisions or to conclude on something that is not actually true. So we're too much on the hypothesis testing. Now let's go down to the p-value. P-value or the probability value of a hypothesis test. The probability of obtaining a sample statistic with a value as extreme or more extreme than the one determined from the sample data. So, decision to rule based on p-value. To use the p-value to make a conclusion in a hypothesis test, compare the p-value with 1 if p is equal to or less than, then reject the null hypothesis. If the p or the population is greater than, then um you have to not reject the null hypothesis. So, failing to reject the null hypothesis doesn't mean that you have accepted the null hypothesis as true. It simply means that there is not enough evidence to reject the null hypothesis. If you want to support a claim, state it so that it becomes the alternative hypothesis. If you want to reject a claim, state it so that it becomes the null hypothesis. The following table will help you interpret your decision. So the first column is we have the decision and then the claim. So in rejects the null hypothesis, it should be that your research does not have enough evidence to reject it, and then there is enough evidence to support the claim. So now let's go down to parametric test for difference analysis. One sample t-test. It is used to determine whether a sample mean significantly differs from a known or hypothesized population mean when the population standard deviation is unknown. But we have to met the assumptions. We have four assumptions in this certain parametric test. First is the sample is randomly selected from the population. Second is the variable is measured on an interval or a ratio scale. Third is the data come from a normally distributed population or the sample size is sufficiently large for robustness. And then last is observations are independent of each other. So we also have this non-parametric test for difference analysis. One one sample Wilcoxon signed rank. It is used to determine whether the median of a single sample differs significantly from a hypothesized population median when the data are not normally distributions. But again, there are certain assumptions that need to be met. First is data are paired with a hypothesized median or one sample or match to a constant. Second is the variable is at least ordinal or rankable. Third is differences between observations and the hypothesized median are symmetrically distributed. And the fourth one or the last one is observations are independent of one another. Next is we have the parametric test for difference analysis. We have the independent samples t-test. We are going to use this to determine whether the means of two independent groups significantly differ from each other. And the assumptions are the two groups are independent, the dependent variable is measured at the interval or ratio level. Third is each group's data come from a normally distributed population. And the third is the variances of the two groups are equal or homogeneity of variance. And the fourth one or the last one is observations within each group are independent. We also have the Welch t-test. It is used to compare the means of two independent groups when their variances are not equal or heterogeneous variances. We have the four assumptions under this test. First is the two groups are independent. Second is the dependent variable is measured at the interval or ratio level. Third is each group's data are approximately normally distributed. And the fourth one is observations are independent within and between groups. So in non-parametric test for differences analysis, again, we have the Will-Coxon ranked sum test. It is different from the other one. Or Mann-Whitney-U, used to compare whether two independent groups differ in their distributions, typically their medians, when the dependent variable is ordinal or not normally distributed. So under its assumptions, we have the two groups are independent. Second is the dependent variable is at least ordinal. Third is the distributions of two groups have the same shape, and the observations are independent within and between groups. We have also a paired sample t-test. It is used to determine whether the mean difference between the two related match or repeated measures observations is statistically significant. So again, here is the assumptions. The two sets of scores are dependent. Some participants are matched pairs. Second is the dependent variable is measured at the interval or ratio level. Third is the differences between paired scores are normally distributed. And the last one is pairs are randomly selected and observations within pairs are independent from other pairs. So in Wilcoxon signed rank test, it is used to determine whether the median difference between two related or paired or repeated measures observations is significantly different from zero when the data are not normally distributed. Here we have the assumptions. The two sets of observations are paired or dependent. Some participants are matched pairs. The dependent variable is at least ordinal. Third is the differences between paired observations are symmetrically distributed. And the fourth one is pairs are randomly selected and are independent from test. Now let's go down to parametric test for difference analysis. One-way analysis of variance. It is used to determine whether there are significant differences among the means of three or more independent groups based on one categorical factor. And these are the assumptions of one-way analysis of variance. The first one is the groups are independent. Second one is the dependent variable is measured at the interval or ratio level. The third is the data in each group are approximately normally distributed, and the variances of the groups are equal or homogeneity of variance. And the fourth one is observations are independent within and between groups. Next is we have the Kruskal-Wallis test. It is used to determine whether three or more independent groups differ in their distributions, typically their medians when the dependent variable is ordinal or not normally distributed. And its assumptions are the groups are independent, the dependent variable is at least ordinal, the distribution shapes of the groups are similar for valid median comparison, and observations are independent within and between groups. We also have the post hoc analysis. It is use this when you found a significant ANOVA result and want to know which group differ. Turkish HSD, most common controls type 1 error. Games Howell, best when variances are unequal or homogeneity of variances is violated. Since ang Kruskal-Wallis is non-parametric, use pairwise comparisons with adjusted p-values. Now is let's go down to chi-square goodness of fit test. It is used to determine whether the observed frequencies in one categorical variable significantly differ from the expected frequencies based on a hypothesized distribution. Its assumptions are data are frequencies 9 counts, not percentages or means. Categories are mutually exclusive. Each case fits in only one category, and then observations are independent of each other. And an expected frequency in each category is at least 5 or most categories greater than or equal to 5 with no very small expected. Now, let's go down to the parametric relationship analysis. We have the Pearson product moment correlation coefficient. It is used to measure the strength and direction of the linear relationship between two continuous variables. And they also have and assumptions that need to be met, which are both variables or continuous or interval or ratio. The relationship between the variables is linear. Variables are approximately normally distributed when there are no signs outliers and observations are independent. We have also the Spearman-Rank correlation coefficients or RHO rule used to measure the strength and direction of a monotonic relationship between two variables when data are ordinal or not normally distributed, or when the relationship is not strictly linear. Its assumptions or variables are at least ordinal. Relationship is monotonic. As one variable increases, the other tends to consistently increase or decrease. The third one is observations are independent. And the last one is no excessive ties in the ranks or ties are handled with appropriate corrections. To proceed, we have this Kendall's Tau B, used to measure the strength and direction of association between two ordinal variables, adjusting for ties in the data, and is especially useful for small samples or many tied ranks. Its assumptions are both variables or at least ordinal. Observations are paired and independent, and the relationship is monotonic as well. As one variable increases, the other tends to increase or decrease consistently. Now we have the chi-square test for independence. It is used to determine whether there is a significant association or relationship between two categorical variables in a population. Its assumptions are both variables are categorical. Data are frequencies counts in each cell, not percentage or means. Observations are independent, where each respondent appears in only one cell. Expected frequency in each cell is at least 5, or at least most cells greater than or equal to 5, with no very small expected counts. Now we have the point biserial correlation for non-parametric tests for relationship analysis. It is used to measure the strength and direction of the relationship between one continuous variable and one truly dichotomous variable. Its assumptions are one variable is continuous, second is the other variable is genuinely dichotomous, and the third one is the continuous variable is approximately normal distributed within each group of the dichotomous variable. The fourth one is the relationship between the continuous variable and the dichotomous groups is linear. And the fifth is observations or of relationship. To proceed, we have the regression analysis, a family of statistical techniques used to model, predict, and explain the relationship between a dependent variable and one or more independent variables. So, simple regression analysis used to predict the value of one continuous variable or the dependent variable based on one continuous predictor or independent variable and to determine whether a linear relationship exists between them. So from in simple regression analysis, we also have assumptions. These are the relationship between x and y is linear, observations are independent, residuals are normally distributed, homoscedasticity or residuals have constant variance across levels of x, and then the independent variables is measured without error. Now we have the multiple regression analysis. It is used to examine and predict the value of one continuous dependent variable from two or more independent variables. Strongly, each predictor is related to the outcome while controlling for the others. And here are the assumptions. Linear relationship between each predictor and the dependent variable. Second is independent observations. Third is residuals are approximately normal. Third one is homoscedasticity or residuals have constant variance across predicted values. And then no multicollinearity or predictors are not excessively correlated with each other. And then predictors are measured without serious. Thank you very much for listening, and I hope you learned well and I made it easy for you to understand. Thank you so much.